Good morning, all. So, we have completed our tour of probability theory, which is this abstract model, this side of the divide, of where data might come from. We started out by just talking about descriptive statistics, meaning I've collected some data, how might I summarize them in order to just talk about what they look like, without regards to a model. We then moved to this probabilistic model, this abstract model of where data come from and what the probabilities of different data sets would be given a particular probabilistic model. So now we need to come back to data and say, given these data that I've collected, what probabilistic model do I prefer? What parameters does it likely have? What parameters does it likely not have because the data are too much in conflict with that choice of parameters? In other words, we're moving on to statistical inference. So, as an example, you collected some data, they had a sample mean. A sample mean is a description of the data you have in hand, and it is extremely unlikely to be the same, identical to the population mean, meaning the mean of that theoretical model that you have in the back of your mind. You don't know what that theoretical model's population mean is. Maybe you have a theory that its mean is 0 or 50 or some number. So that would be a model you could test and say, are my data consistent with that abstract model? Or you might want to say, I collected these data, I think they come from this sort of a model, but I don't know what the model's parameters are. I don't know the population mean. My model is just that that population is Gaussian distributed, but I don't know what its parameters are. But I'd like to have some bounds on what its mean might be. I have a sample mean, so the population mean is probably near it, but how near it? So in order to use that, we have to use some behaviors of the statistics that we calculate. So, I think we said this, but the word statistic just means I collected some data and I did some mathematical operation on them to give a summary of some kind. So anything you take raw data and then do something with it, like add it up and divide by n, or compare it to its sample mean and take the sum of the average of the squared distances and divide by n, otherwise known as the sample variance. Or anything you calculate of that sort is a statistic. And so statistical inference is to take those statistics and infer something about the population and infer how much you trust that estimate of the population and so on. So for example, we might collect a sample and calculate its sample mean. So that's a statistic. Then we want to say, what does that tell me about the population from which they're drawn? Its mean presumably is close to that number, but in order to make an inference, you want to not just say, well, okay, I think it's close. I don't know what close means. You want to say how close. And you have a reasoned justification for how close you say that it is. So as it happens, and as we'll talk about as we go along, when we do that, we'll be using some aspects from probability theory. So for example, in probability theory, if you take a number from a distribution, that probability distribution has aspects that we've talked about, like it has a mean, meaning an expected value, and it has a variance or a covariance if it's multidimensional, and so it has properties of what you expect of numbers that you draw from it, what they'll be on average, how far they'll be from that expected value on average. That would be the variance. We've also determined properties of those probabilistic concepts. So for example, if I draw from a distribution and then I draw another independent number from those distributions, and I take those two numbers and sum them, one of the last things we did last week is what are the properties of that sum of two independent random variables? Well, their means add and their variances add, and I proved that to you. So when you calculate, when you calculate this thing, right? When you collect data, and then compute an average, what's going on under the hood? Well, your model may be that each of your measurements were probabilistically independent from every other one. So we often assume that in psychophysics, where you do a bunch of trials in an experiment, and we act like every trial is independently of each other. And so I might take your performance, your magnitude estimations, or your your proportion correct or whatever, by taking individual trials, add them up, and dividing by n. And I often make the assumption that these measurements are noisy, and that the noise on one trial is independent of the noise on the next trial, which means that this thing you're calculating has kind of two hats. One hat is, these are the numbers, I collected them. Okay, I have them. I would like to summarize them for you, so I'm going to add them up and divide by n. But we also have a theoretical description of where these numbers came from, which is to say we think we got these data from a probabilistic device, which is the world leading to a human or a rat or a neuron to produce numbers on multiple trials. And that theoretical model may act like these trials are independent, and they may act like they have a particular form of distribution, binomial for button presses, normal for measured noisy numbers, Poisson for spikes. And we're taking a bunch of draws from this urn and adding them up and dividing by n, and that's how I got my sample mean. In which case, I want to take properties of the probabilistic model and work with them. And things like the mean of the sum will be the sum of the means, and the variance of the sum will be the sum of the variances. And that when I multiply by 1 over n, I am multiplying the mean of this thing, the expected value of this thing, by 1 over n. And when I multiply by 1 over n, I'm taking the variance of this thing and I'm multiplying by 1 over n squared. Okay? Things like that. These are things that we derived for theoretical probability distributions. So where we're headed over the next week and a half is to combine descriptive statistics as we've discussed them, probabilistic models as we've learned about them, and say, okay, once I gather data, what can I safely conclude about that data? How much confidence do I have in the statistical description of the data that I got? What can I conclude about that, about the population mean, where it is, how close to that it probably is? And later on down the line, suppose I don't have one model of the data, suppose I have several and I don't know which one's correct. And so can I compare alternative models using my data to discriminate between which of these models is more likely to be true? So as we proceed, we'll be using aspects of probability theory, such as the way sample means behave, the way sample variances behave. We'll be using aspects of probability theory like, even though my model isn't that each datum came from a normal distribution, when I add them up and divide by n, as long as n is reasonably large, this may not be normally distributed, but this will be pretty close to normally distributed. That's the central limit theorem. That was one of the aspects of the normal distribution, is that almost anything looks like a normal when you collect enough data. And so we'll be using probability facts in order to develop our ability to make conclusions from data. Conclusions being about parameters, so inferring parameters of a distribution, or comparing models. Okay. So, so again, our model of running an experiment is there is some kind of theoretical model that describes the world in which we're doing our experiment, which could be normally distributed or Poisson or some other thing, depending on your model and the type of data you're collecting. If you're collecting multiple observations on each trial, height and weight, whatever, so maybe it's a multivariate normal. So you have this idea that there's some theoretical urn from which you're drawing your trials. You may not know its parameters. You may not know this number or these four numbers, covariance and mean. Multivariate mean. You may not know them. You may want to infer about them. But you draw a bunch of data from them, you get data. The data look like they came from a model of that nature. And from these raw data, you can get things like sample average and sample covariance. And now, having done the sampling, we want to reverse the arrow and make an inference about what's the model from which we drew them. And as we proceed, there will be kind of two traditions that we're going to cover, one way more than the other. So the two traditions are doing things fully probabilistically, meaning you come to the problem with some expectation, some prior knowledge about what this world might be, and what values for it are reasonable and what values of it are unreasonable. You then collect some data and you say, okay, so what more do I know about this now that I've collected data? So that's the Bayesian perspective, using Bayes' rule, meaning I had prior knowledge, and then I use Bayes' rule to combine that prior knowledge with the new data in order to get a posterior distribution that's hopefully closer to my data than my expectations were before I collected the data. So that's one tradition. We'll spend much more time on that one. That's, let's say, the more modern perspective. When Arrow's up here, I'm sure we'll give a longer spiel about that. I'll be brief. But I'm also today, probably today, going to cover the more traditional perspective, the one that is in every paper and that we're all taught to use, which is the Frequentist Statistics description, the Fisherian description, where the way you make conclusions uses a very different kind of approach, and I'm not going to talk about it until I get to those slides, but not the Bayesian perspective, but it's the one you see in every paper with every conclusion that says, I conclude this, parentheses, p less than 0.05. Okay? It's what we were all taught if you took an undergraduate stats class. That's what you were taught. And so we'll talk about that a little here, and I'll talk about the meaning of it, but unlike a typical class whose title is statistic, I'm going to brush past it in kind of broad overview with a few examples without spending all the semester about what are the 50 different tests one could do, and when do you use this one versus that one, and when do you justify the assumptions of this one, and how do you do that. That's a different course, but at least we'll give you a view of how to think about that and how that is distinguished from the Bayesian perspective. Okay, so in order to say, if we want to do inference, from data based on theoretical thing, we'll be using various facts. So one of those, obviously, is the central limit theorem. So the central limit theorem basically says when you draw samples from almost anything, no matter how that thing is distributed, as long as it's at least slightly well-behaved, and slightly well-behaved is the data are coming from a distribution whose variance is finite. There are distributions with tails that are so big that when you compute the probability, you compute the expected variance, the covariance matrix or the variance, it doesn't converge to get an infinity. And those things are not well behaved and will not satisfy this. But as long as it's kind of a well-behaved distribution, even if it's discrete, even if it doesn't take on very many values, like a binomial, by the time you average over lots of them, it gets to looking more and more like a bell curve. So here's an example where I'm drawing from a uniform distribution between, I don't know, minus 1.8 plus 1.8. I think that was probably in order to have it have mean 0 and variance 1. Yeah, exactly. And so this is a uniform distribution. Actually, this is a bunch of samples from a uniform distribution. So the probability distribution is absolutely flat. But when we collected this many samples, it's got some noise. And that's what a single draw from the distribution looks like. Sometimes it's low, sometimes it's high, sometimes it's in the middle, and all values are equally likely. However, if we took two independent draws from this distribution, just pick one guy and then throw them all back in a hat, pick another guy, and add them up and divide by 2, divide by square root 2 because we're trying to keep the variance the same, then you get something that looks like this. Now, why does it look like a triangle? What is the distribution of the sum of two independent numbers? What do you do with the individual distributions to get the distribution of their sum? You convolve them. Okay? Back to linear systems theory. Convolution is you take one and you run it over the other and do a dot product as you go along. Okay? You take a rectangle and another rectangle, and you run one past the other. You get 0, 0, 0, now you get a small number, more, less, less. You get a triangle. Okay? The reason you get a triangle is a rectangle convolve with itself as a triangle. Okay? And now you're going to convolve a triangle with a rectangle, which is going to smooth out the corners. And then you can convolve a rectangle with that smoothed out corners triangle, and you can get something even more smoothed out. And if you do it over and over again, it starts looking like a bell curve. And you don't have to go do it very often for a uniform distribution for it to look pretty close to a bell curve. Okay? So that's the central limit theorem. It says if you add up more and more of them, it gets to be looking more and more like a bell curve. Now, this is not the sample average because I'm not dividing by n. I divided by square root of n. And that's just for the graphics of this slide. Why am I doing that? Why square root of n?
To keep the variance.
Yeah, now spin that out a little further. Why does that work?
Because independent samples, when you sum them, the variance of the sum.
Okay, so let's do that for just 2. So this has a variance, which is 1. Because we make variance be 1. Sigma is 1, sigma squared is 1. Okay? Okay, we took 2 independent draws. So their variance is add. So their variance is 2. Okay? So I'd like to make the sum have variance 1 by multiplying by a constant. So that the shape will look like that. The width will be about the same as that. So the variance is now 2. So if I took the sum and divided by 2 to make a sample average, what would the variance get multiplied by? So if I did u1 plus u2 over 2, compared to u1 plus u2, when I divide by 2, what am I dividing the variance by? When you multiply a random number by a half, a random variable by a half, what are you doing to its variance? Multiplying by 1/4. Okay? When you multiply by a half, you squeeze the distribution by a half. The standard deviation goes by a half. But the variance is the square of the standard deviation. So you multiply the variance by a quarter. Okay? So we want to keep the variance at 1, period. We don't want to divide by 2 and get a sample mean. We want to do this other odd thing, which is divide by square root of 2, square root of 10, and so on. So this was just a graphical thing, so these guys all have the same variance. Okay? So that's all. This picture was done just to say if we have the same variance, but we're doing it by combining more and more samples, it looks more and more like a bell curve. And by giving it constant variance, by dividing by square root of 10, we're making these things sort of commensurate. That's all I'm trying to say here. If we had divided by n, we'd be dividing by a bigger number, which means these guys would be getting skinnier. Okay? Keep that thought in mind. That will return in a few slides. Hence, adding up and dividing by n makes the distribution get narrower, which is a good thing. It means you know more when you average more things. That will come back extremely shortly. But let's keep with the central limit theorem. Here's a binomial random variable treated as numbers. Okay? Coin flip. Heads is 1, tails is 0. I'm making up the correspondence, but who cares? Okay? So if it's a fair coin, it's 50-50 you get 0, and 50-50 you get 1. So on any given single toss of the coin, you either get 0 or you get 1. It does not look anything like a bell curve. But if you flip the coin 4 times and then count the, average number, so now we're not dividing by square root, by the way. Now we're dividing by n. Okay? So you flip the coin 4 times and say, what proportion of heads did I get? Well, you either got none, 1, 2, 3, or 4. And there's 3 ways to get, let's see, how many ways to get this? 1, 0, 4, 1, 3, 2, 2, 3, 1, 4. Oh, sorry, no, am I doing that right? No, I'm not doing that right. Yeah, say what I mean. Because I just was thinking about the rolling dice example, which was the wrong one. Okay, so I'm going to flip the coin 4 times, so I can get head, 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 tail, head, 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 tail, head, tail, tail, head. Because what am I doing? That's another word I need to do. Head, head, tail, head, 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 tail. This is going to keep going, but you see that I got one of these. I got 4 where I only got one tail. I'm going to get 6 where I get two tails. I'm going to get 4 where I get 3 tails, and I'm going to get 1 where I get 4 tails. Okay, 1, 4, 6, 4, 1. That's what you're looking at here, 1, 4, 6, 4, 1. Okay, so it's just counting. That's the binomial distribution. And the binomial distribution, where you get these numbers like 1 and 4, is the binomial distribution is the probability of getting n, let's do m tails given n tosses is from n choose m combination probability where p is probability of tail to the m 1 minus p to the n minus m. This will be on a subsequent slide. This is just the coin toss distribution. This piece is just counting how many ways you can get, for example, 1 out of 4 or 2 out of 4. Okay? How many have never seen a combination before? Anybody? Okay. So to spell this one out, just so you know what it is, first of all, I define n factorial, which means n times n minus 1 times n minus 2 times ... times 1. Okay? And this is n factorial over m factorial n minus m factorial. Horrible formula you'll never do by hand. Okay? And how do you derive that? You think about what are all the ways you could have, where's my eraser? Just on this side, all migrated. So looking at this counting argument again, actually I don't want to erase too far, I have some space to work. Okay, you don't want to have to do this after 4. You don't even want to do it for 4 because there's 16 of them. The more times you toss it, the harder this gets. So let's look at this formula and then let's think about how it worked out this way. So this is n times n minus 1 times ... 1. And over here is m times m minus 1 times ... times 1. And then n minus n minus m minus 1 ... 1. Okay, that's what the formula says. Now, this is going to cancel out a lot of the stuff on top. Right? Because there's a 1 and a 1 and a 2 and a 2 and a 3 and a 3. There's going to be a lot of cancels. So another way to think of this fraction is n times n minus 1 times ... times everything except what got canceled out. N minus m plus 1. And then this guy doesn't get canceled out. M minus 1 ... 1. Okay. Now let's think about this problem and why it would lead to that horrible looking fraction. Okay, what is this problem? We've got n twin quizzes. Okay? And we are going to decide that, say how many of these orderings of n h's and t's have m t's in them. Okay? So let's think about that. We're going to, I haven't done this so long and I didn't think about it before coming here, so now I've got to reconstruct the argument in my head. So I've got 1, 2, 3, the numbers up, 1 up to n. And I'm going to have the first bunch be called T and the rest of them be called H. So this is up to there's a little m right here. Okay? So, if I took the numbers 1 through n and said, I'm going to talk about all possible orderings of the numbers 1 through n. Okay? So, how would I do that? Well, I'd pick one of them, any one of them, and put it first. So, I have n choices for what I put first. And then I have n minus 1 choices left over that I could put as the second position. And then I have n minus 2 choices that I could put in the third position, ... Okay? So that's how many orderings of n things exist. That's n factorial. Okay? We don't care about the orderings of everything. We just care about the orderings of the tails. So I'm not going to go all the way down. I'm going to just do the tails. Did I do the right canceling for this way of thinking about it? I may have, let me think about that for a second. M, I canceled n minus, yeah. Yeah, so there's no, yeah. So I'm just gonna say, suppose I just pick the tails ones first. So there are m tails, so I'm not gonna need the whole factorial. I'm gonna go down to n minus m plus 1. So that's m things. Okay, so now I've picked which positions need to be tails. Because I want to say how many combinations give you m tails. So I've picked which positions, but that's really silly because in this list, I might have, for example, position 7, position 5, position, all the other ones. Or I might have in here position 5, position 7, and these ones matching. Which is to say, these are both in there, but that's silly. They're exactly the same series of heads. They're a head, or this, series of tails. There's a tail in this position, this position, and in positions 5 and 7. So I have to discount all these orderings, because they're all the same. They all involve the same exact tossings of the coin. Which means I have to divide by the number of these. And for any given ordering, for any given choice of which ones are tails, the fact that I have them down multiple times because I'm acting like they're in different orders, but that's irrelevant. I have to fix that. So I have to divide by the number of these, which is exactly this. Okay, so that's just to give you an intuition of why the formula. In any case, that's where you get these heights for coin tosses. And those heights, when you get to more coin tosses, you notice it's looking more and more bell curve shaped, even though it's a discrete distribution. And here's 64, and it's looking more and more. So there are two things to notice here. One is central limit theorem, which is to say this is looking more and more like a bell curve. It's an approximation. It'll never be perfect because this is a discrete distribution and the normal is continuous. But there's another thing to notice. This has high variance. This has lower variance. Lower still. Lower still. Why does it have lower variance this time when it didn't last time? When I mean last time, I mean literally this slide. Okay, that one, we kept all the variances the same. This time we didn't. What's different on this slide? Yeah, no, why? What's different about the computation in this slide than the previous slide? Why is this getting narrower? Yes. Each one of these is the proportion of tails, meaning add them up and divide by n, not divide by square root of n. So that extra square root of n is reducing the variance by n and reducing the standard deviation by square root of n. So when you compute averages, two things happen. When you take the sample data, you add it up and divide by n, first thing that happens is, even if it wasn't normal to begin with, it'll start to look normal if you collect enough data. And second is that the width of that distribution, the distribution of sample means of size 64. So if you went out and did your experiment, collected 64 data points, but oops, you decided, let's try it again, collect another 64 data points, and say how sample means vary, they don't vary as much as the raw population does. Raw population has big variance. The sample variance is smaller. And the more data you collect, it gets smaller and smaller at a speed of square root of n. So that's why you collect more data, because your estimate of the population mean, which is a half, which you are estimating by collecting your data, when you add them up and divide by n, are on average getting closer and closer to the thing you're trying to estimate. So say you don't know this coin is fair. You're testing whether this coin is fair by tossing it a bunch of times and seeing whether you get approximately half heads. Well, if you only do it once, you don't learn anything. If you do it 4 times, well, you might get half, but there's a very good chance that you'll get something really far from half. But if you toss it 64 times, you might get 0.6, not very often. And you definitely will not get 0.8. So if you tossed it 64 times and actually got 0.8, that would be very strong evidence that it wasn't actually a fair coin. So I'm starting to work towards the logic of statistical inference, which is we didn't know the population was 0.5, but if it was 0.5, it would behave like this. And so if I get something way over here, that's good evidence that it wasn't drawn from this distribution and that there was something else going on under the hood, other than, oh, it was a fair coin. Bills remaining. Is it build? Oh, that's 256. Narrower still. Okay. Now, let's talk mostly the rest of today about the frequentist way of doing statistics, the standard one that if you took an undergraduate stats class you've seen. And this horrifying thing is just to say that if you live in that world, you live in a world where you think about the kind of data you have, you try to search through the literature for the statistical test that people think is appropriate for that form of data and that particular question. And so you're kind of in this flowchart of which of these millions of frequentist statistics should you use. Should you do a z-test, a t-test, a chi-squared test, an f-test, whatever? Should you do an ANOVA? Should you do some non-parametric thing, et cetera, et cetera, et cetera. This class, that's a semester. This class, we're not going to do all of that, but try to introduce the logic behind the simplest versions of them. So let's start with the simplest one. So suppose, and that's the z-test. So z, by the way, in stats, refers to the standard normal distribution, to the normal distribution, univariate, mean 0, standard deviation 1. Okay? So suppose I have some data about a drug, NZT. I think Pascal Walsh made up this acronym. I don't know. So it's some drug that somebody proposes that it improves IQ. Okay? So some facts. So some facts to begin with. The IQ test is a standardized test that gets standardized in such a way that supposedly across the normal population, it's a number after you take the test, and that number on average sampled over the normal population has mean 0, and it's literally scaled. The data are cooked in such a way that the population mean is 100, and the standard deviation is 15. So an average IQ is 100, 115 would be one standard deviation above the mean, 85 would be one standard deviation below the mean. So we take that as fact, that is true of the general population. And now we're going to ask, if we give this drug, do IQ scores go up? So the Fisherian way of doing things relates to the way I was talking about the distributions I was showing you just a moment ago. So the logic I was describing a moment ago was, if I flip a coin 256 times, and if it's a fair coin, meaning it comes from a binomial distribution 50-50, heads, tails, then I have a probabilistic model, and I know the distribution that I should get for samples of 256, take an average of what proportion are tails, which is on average I should get 128, but sometimes I get bigger, sometimes I get smaller, and it'll be relatively narrow around a proportion of 50%. That getting a proportion of 80% is extremely unlikely. It can happen, but its probability is very low. So in the Fisherian approach, you start with kind of an anti-hypothesis. So this is a hypothesis, and the notation often is it's your hypothesis H1, meaning the thing that I'm testing, something happened. And you always end up distinguishing it from a hypothesis where whatever your manipulation was didn't do anything. So that's often referred to as the null hypothesis, or H0, which in the case here means this drug does absolutely nothing. So as I said, IQs are scaled so that they have a known distribution. Gaussian, mean 100, standard deviation 15. So this is the population from which you are drawing before you use the drug, and it is also the population from which you're drawing after you use the drug if the null hypothesis is true, and the drug is, good in claims. We know the distribution of a single measurement. We can derive from it the distribution of run the experiment on 50 people and take an average, and it'll be exactly like this because you're taking an average. You'll still get an expectation of 100, but because you're adding up 50 random samples and dividing by 50, that means you are going to get something that's narrower by the square root of 50. Okay? And so we know what that distribution is also. It's just using exactly the math that we did last week, in fact. If you're adding a bunch of identically distributed random numbers, they are all normal to begin with, but even if they weren't, they'd be normal afterwards. Because you're adding up and dividing by n, that means you're adding up a bunch of things with the same mean, so you're getting something whose mean is n times bigger, and then you're dividing by n, so you're canceling. So the expected value should be the same. And because the variance is add, so you've added 50 of them together, so the variance just went up by a factor of 50, but then you divided the sum by 50, which means you divided the variance by 50 squared. So the variance went down by a factor of 50 when you took that average, which means the standard deviation went down by square root of 50. That's the square root of n. So calculating descriptive statistics, why we go out and collect samples and why we collect more trials in one experiment than another is because we get more precise. Our estimate gets a smaller standard deviation. Aside, I don't think we defined those words precisely in this class before. In our field, we refer to a statistic as being accurate and or precise. Precise means the distribution of that statistic is narrow. Imprecise means it's really noisy. Accurate means on average it's saying the right thing. Inaccurate would mean that it has some bias. That even though you're doing some descriptive statistic that should be telling you about some population variable, that on average it actually isn't telling you the right thing. And so is biased in some sense. And we'll talk about bias for some statistics, probably not today, but probably on Thursday, I think, is when we'll hit those slides. Anyway, so as I said, in the general population, the IQ is not only known to be, is designed to be distributed normally with these population values. And so now we're going to do an experiment, and we give this drug to 30 people and test their IQ. So there's the IQ distribution again with this mean, oh God, why didn't I get rid of these builds? I hate builds. With these values. And so we can then calculate that if we take 30 people, if the drug had no effect, if the null hypothesis is true, then we're just taking 30 draws from this, because the drug didn't do anything, so it's the same as this. And we're adding them up and dividing by n, which means that the sample average, according to the null hypothesis, will also have mean 100, and will have standard deviation 15 divided by the square root of 30. It'll be narrower because you're adding up 30 numbers and dividing by n. So we gather 30 numbers. And so here are 30 numbers, histogrammed. Okay? This is raw data, what we got. And they look a little shifted to the right, and so you would want to say, okay, maybe the drug worked. So they have a sample mean noted in green here. It's, I don't know, 107 or 108. Notational thing to point out that I pointed out once before is that in this version of statistics, we often use Greek letters to talk about the underlying theoretical distribution, the probabilistic model. So that would be mu and sigma. And we use Roman letters for properties of samples. So even though in this course, earlier in the semester, when we defined the sample mean, we often threw mu around, in this literature you usually see x bar for the sample mean, and s for the sample standard deviation, rather than s instead of sigma. Okay, so x bar is just add them up and divide by n, and we got a number that was bigger than 100, so maybe our drug works. So x bar is a sample mean, which is to say it is, if the null hypothesis is true, it's also a random variable. It's a description of a random process that can spit up different numbers if you do it over and over again. So if the drug is completely ineffective, x bar is a random variable, and we've already talked about the way it should behave. Its mean, if the null is true, should be 100, and its standard deviation should be square root of 30. Okay? So if we subtract 100 from it, x bar minus 100, even is 100, x bar minus 100 is another random variable. It's a random variable that still has a standard deviation, which is 15 over the square root of 30, but now has a mean, which is 0, because I've subtracted off the mean of x bar from it. Now, if I divide by this standard error, if I divide it by 15 over square root of 30, which is what the standard deviation should be, so now we have a new thing whose standard deviation should be 1. Right? Standard deviation was 15 for a single measurement. I took 30 measurements, took an average, so the standard deviation is now 15 over the square root of 30. So it's about a little under 3. Okay? So I got a new standard deviation. Now if I divide it by that number that's like 3, I now have a new number whose standard deviation should be 1. So by subtracting the population mean and dividing by the population standard deviation, which in this case is known, not the population standard deviation, but the standard error of this averaging process, which is the population standard deviation divided by square root of n. By doing all of this, I've converted from a random variable whose mean is 100 and whose standard deviation is 15 over the square root of 30 to a new random variable that I will now call z. Why? Because it's now a standard normal. It now has mean 0, and now has standard deviation 1. And so I get this number, which is called the standardized score. So this was a process which has a probabilistic model that if you believe the null hypothesis, we know what it is. This calculation converts it to another probabilistic model, which is a standard one. And so every student who ever took a statistics course bought a book that at the back of the book had tables of Z. Tables of what did you get. So I can't remember what's on the slide, so I'll step ahead of all this on the projector and just do this. So then you have to decide, well, what happened and how do I interpret it? So again, we had something which, if the null is true, every individual measurement had a mean of 100 and the standard deviation was 15. We then averaged 30 samples. And that will lead to something that looks like still centered on 100, but now it's 15 over the square root of 30. The square root of 30. We then calculate Z. The standard error here is sigma over square root of n. Okay? And that gave us something who still looks like a bell curve, but now the middle is 0 and the width is 1. And so we got what's called a z-score. Okay, so what used to be 108 will now be 8.3 divided by something a little less than 3. So it'll be 2 point something. So we got some number. Okay? And we say, oh look, it doesn't look very likely. Is that so rare that I'm willing to say, oh, the null couldn't be true because I got something that was so discrepant? So the logic is, oh, there's more to this build. Let's finish the build. Did I finish the build yet? No. Now I finished the build. Okay, so I compute this standard error, which is, as I said something a little under 3. I then compute the, okay, let's get to error bar in a minute. We compute the z-score, which is a pretty big number, it turns out. Which is, way off in this tail. And so we want to say, how unlikely is that? So in order to do that, we have to decide about what we want, what kind of errors we're willing to make and how often we're willing to make them. So, hold on a second here. I just want to look at upcoming slides and see how much I'm jumping ahead of what's up on the screen. Oh, yeah. I'd rather show it now, even though it's coming up in a slide. Yeah.
How would you do this if you don't have a big population mean first place?
Coming up.
Okay.
Coming up. That's called a t-test, and I'll talk about it in just after the break. Yeah. So we're starting with the simplest possible example where you actually know the null hypothesis complete. And so the null hypothesis is, I know the mean, I know the standard deviation. So we're starting with an example where it's a test that was designed to be known. It's a dumb example, you never meet it in real life, or almost never, except for coins. But it's the simplest one to describe the logic, and then we'll generalize it. Okay, so you're going to do two things now, which is try to estimate how much to trust the effect you got, and to decide whether the null hypothesis is true or not. So let's talk about the latter case first. So there's two things we're doing. We're estimating a population parameter. Our null hypothesis says the population parameter is 100. Our data says it's 108. And so we could say, well, I think it's closer to 108, but how close do I trust it to be? And do I believe 100 anymore? So let's talk about, do I believe it's 100 anymore? Okay, so there are two possible worlds that could be happening under the hood that you are interested in. One is the null hypothesis is true. The other one is the null hypothesis is not true. When you're done collecting your data and deciding what you want to conclude, you're either going to say, you're either going to accept H0, meaning I don't have enough evidence to tell me anything otherwise, or you're going to reject H0. So in terms of just making a decision about what your data allows you to conclude, there's only two states of the world that we're considering, which is the drug doesn't work or the drug does work. And there's two conclusions you can make. The drug doesn't work, the drug does work. Okay? So this is a correct accept. This is a correct reject. And there are two kinds of errors you can make, which is the drug was worthless, but you concluded it was worth something. I hope I get, I think that's called type 1, but I have totally forgotten the nomenclature. Yes. Yeah. So the literature names these as type 1 error and type 2 error, and gives them Greek letters. And what was decided to do, and what the entire world of science does, is it decides, I don't want to make this mistake very often, And so I'm going to set a level of how often I'm willing to make this mistake. Now that's one we can easily estimate and put into our model. So this mistake is the null is true, meaning the model that I've been working with all along is true. Which means that my data collection, once I convert it to a z-score, looks exactly like this. And I will reject the null if I get an effect that's big enough to look rare. And if rare happens once in a while, that'll be the probability of making that mistake if the null is true. And so the standard significant enough is alpha equal 0.05. That's just what the world, what every journal requires. It's just the way statistical lore has been for quite a long time, which has led, of course, to this huge replication crisis that's going on in many fields where people are replicating studies and having them no longer come out with the same results. But regardless, there's one last niggle to talk about, which is we're talking about this drug, and I'm hoping that it'll improve IQ scores, but it's a drug. It can do all sorts of things. Might make them worse. So generally, the null hypothesis is that it's equal to 0, and the alternative is that it's different from 0 in either direction. That refers to getting numbers out here and getting numbers out here. So that's referred to as a two-tailed test because it's both tails of the normal distribution. And generally people do this, although occasionally they will do a one-tailed test, and there's issues around that because those are easier to reject and less powerful and more likely to make mistakes. So I won't go there today. But the two-tailed test says, I want a 5% chance of making this mistake, rejecting when the null is true. This is the way the null behaves if you gather n data points and divide by n. And so so in order to maintain a 5% chance of ending up in the tails, that means I want 2.5% over here and 2.5% over here. And so then you look up in the back of the books and say, where do I put this boundary? What z is big enough such that the chance of getting bigger than that, either on the right or on the left, adds up to 5%. And that number, it turns out, in the back of your book is 2, approximately 2.0 something. I forget the exact number. Okay? So in other words, the standard normal distribution, the probability of getting a number bigger than 2 or less than -2, the probability of that event happening is 5%. Okay? And so the statistical inference is the procedure that basically all of science tends to follow is that if I was doing a z-test, if I have something that acts like z, meaning I've taken my data and done some manipulation on it such that the behavior of this thing should be like a standard normal distribution, mean 0, standard deviation 1, if the null is true, I will reject the hypothesis that the null is true if I get an answer for my data that's bigger than 2 or less than -2. And right here, we got a number that's 3.03, and so we will decide, oh yeah, NCT works, p less than 0.05. In fact, 3.03 is so far into the tail that I'll probably specify a p even smaller than 0.05 because it's way in the tail. Or you can say, my number is 3.03. So what is this area? A -3.03. What's this area? So actually go off and calculate that. And then I'll say p equals, and I'll put that number. Okay? So, yeah, I messed up.
My question is, how has that 5% of criteria been calculated?
Well, first of all, the 0.05 is a sociological standard with no justification whatsoever. We, as a multitude of fields, have agreed that you're allowed to publish if you do your experiment and get less than 0.05, and you're not allowed to if you don't, which has many negative sociological effects, which is all the ones that were greater than 0.05 and ended up in somebody's file cabinet, and people do experiments until they get less than 0.05, and then they start writing papers, which is a selection bias. one could talk about this. We could have a whole semester discussion of these issues because they're big. 0.05 is arbitrary. The exact p-value is a calculation, which is what's, I should switch colors to something. My three, okay, let me draw a bigger one so we can see it. So here we are with the standard normal again. Here's 0 and here's 1, and I got 3.03. So I can calculate this area. And I can say P equals, and it's going to be something like 0.001. It's going to be a really small number. That it's getting 3.3 or bigger, or on the other side, if the null is true, is an extremely rare event. It's so rare that you will no longer accept the null as truth and assume that the drug is doing something. Okay? So that's the logic of the test. Now, the other thing that standard statistics does is it says, here's how much I trust my data. Meaning, I'm also going to report my sample mean. I'm not just going to report that NZT had an effect. I'm going to talk about how big the effect was. Meaning, I'm going to report X bar. Okay? But then I have to say, okay, but I don't know that the drug increases IQ by 8.3 points. Maybe it increases it by 9 points. Maybe it increases by 7 points. If I ran it, an infinite number of times. I only collected 30 people. So I don't really know how much it works. Which means I not only need to report 8.3, but I have to report how much I trust that number. It could be bigger, it could be smaller. So, if you had run, if the drug had no effect, and if you were literally taking I guess if you pointed this one, if you had literally didn't know it was 100, and it was, and you got the number 100, you could have gotten numbers that were bigger by 100, plus 15 square root of 30, minus 15 square root of 30, bigger, less. If in this distribution I wanted to discount the ones that are 5%, then I would go plus or minus 2 standard deviations. Now, the standard deviation here is 15. Standard deviation of here is the standard deviation of the process of taking 30 people and dividing by n. So as an estimate of this is actually more precise. It's less noisy by square root of 30. So we give this guy is the standard deviation of this distribution, but we give it a new name, which is on all the slides, which is we call it the standard error, and sometimes write it out as the standard error of the mean, meaning if you collect 30 samples and take a mean, it will bounce around less, and here's how much it will bounce around by. It is a standard deviation, but it is a standard deviation of a statistic, of a summary of 30 samples. Okay? And so what we're saying is if the null is true, on average you'll get 100, but plus or minus, 15 over the square root of 30 most of the time, or 2 times 15 over the square root of 30 really most of the time. And so you'll report your error plus a notion of your average plus a notion of how much you expect it to vary. And you'll say in your write-up what this number you're adding, plus or minus number, is. Okay? Could be plus or minus 1 standard error, which means you're only coming out to one, plus 1 standard error and minus 1 standard error. So you could give this interval from here to here saying it's 100 plus or minus 15 over the square root of 30. Now that happens in our theory, this percentage of the time, that probability is 84%. So there's a pretty good chance, 16% of the time, that you would get numbers even outside there. Sometimes we'll go plus or minus 2 standard errors and plot those on our graphs or plot those in our running text. That means you're going all the way up to this boundary. Oh, God, this isn't working. That means you're going in this area, which is, again, 95%, the one we were using before. So you will often report, oh, my drug gave me 100, where's X bar? There's X bar. My drug gave me 108.3. You might say plus or minus 2.74 to say here's how much I trust it. You might say plus or minus double of that, or plot plus or minus double of that. Do 2 standard errors, because 2 standard errors is the normal cutoff point for the P equals 0.05 test. So that's referred to as a confidence interval. The interval of how confident am I in this sample average that I have computed. I got 108, but I know it's not exactly 108. It could be something else. It being what this drug does if I ran it on an infinite number of people. What the probability distribution is from which I drew 30 people. I can't run that experiment, it's too expensive, but I can say, well, I got 108, but I also know how much they vary, and so I know that it would be within this interval most of the time. Now, there's some backwards logic there. What do you mean it would be in this interval? I got data, I'm going back to population. What I'm really saying is those populations would have given me the data I collected. That is a big flip that just happened there. And it is the big flip that is underneath frequentist statistics. The confidence interval doesn't say what you think it means. What you'd like to say is, I got 108, and because of this manipulation, I think that there's a 95% probability that the true population mean is between 108 plus double of 2.74 and 108 minus double of 2.74. The actual calculation you do isn't that at all. It's if those populations were those values, and I got the data I got, I would be comfortable believing those population values, because I'd be within that 0.05 interval that I would accept, that I would accept those null hypotheses. So it's all kind of backwards. I would like to, IQ is 100, I got 108. I would like to say, oh, here's the distribution that I believe in. But what frequentist statistics does is it says, no, I have this as being the general belief, and then I collected these data, and so I don't think it's that, but I don't know what it is. The yes or no decision from this box is all about rejecting the null. It's not about saying which alternative is true. I don't go look for the most likely alternative. I don't calculate a probability distribution across alternatives. That's the Bayesian approach that we'll spend most of our time on. The statistical approach is, I can't know about the world. I can't know about alternative hypotheses and which ones are more likely and which ones are less likely. There's just no intellectually acceptable way to make a decision about that or make a probability distribution about that. I'm not willing to have a prior distribution that I'm willing to believe in and work with. Rather, I'm going to have the notion of no effect and just ask whether that is unlikely given the data. And then I'm going to calculate a confidence interval around my data, which will be plus or minus a standard error or plus or minus 2 standard errors, where the standard error actually derived from the null hypothesis, or possibly derived from the sample standard deviation of the data. We'll talk about that after the break. One sec. And so what this confidence interval is really telling you, in the language of frequentist statistics, is if the population was 100, I'm outside that interval. If the population was 100 and I collected 108, I would reject that hypothesis. If the population mean was 101 and I got 108, I would reject 101. So the confidence interval, if I use plus or minus 2 standard errors, is all those hypotheses that I wouldn't have rejected. All those hypotheses that are still 95% confidence, consistent with my data. It's kind of a backwards logic. It's not my data proves that one of these hypotheses is true. It's that these hypotheses would not be disproved by the data that I collected. Question?
So the confidence interval is the sample with
plus or minus
plus standard
error. Plus or minus 1 or sometimes plus or minus 2, whichever one you use, you say in your paper or in your figure legend.
And I guess there you wrote 100 plus or minus standard error.
Here, yeah.
Yes.
Yep.
And why because 100 is the
This is the rejection region, the acceptance region, I'm sorry. This is the region, if your data came inside here, you would accept with 2 times. That's how I found these bounds, these 0.05 bounds. That was, if you take this and translate back to here, that's 100 plus or minus 2 standard errors. So if your data falls in 100 plus or minus 2 standard errors, you accept the null. Okay? That's the original test, this part. That's not the confidence interval, that's the test. Okay, well, yeah?
What if the data apparently has a different variance than your null?
Good question. Let's return to how you would test that. Because of course it will have a different sample variance than the population variance because that's a noisy number. The question is, if you're interested in, are my data more variable than I expect, that's another test. It'll follow the same logic as this, but it won't be a z-test.
Probably I'm not testing that, I'm still testing the mean, but it happens that the data I get happens to look very different from the...
Let's return to that when we have the words to talk about it, which will be right after the break. Let's take a break. Okay, so I never did finish this build, but let's not do it.
Everything you wrote on the board is in the next 4 slides.
Oh, I know, I've got that. Yeah, no, it's true. Anyway, so that's the standard logic of frequent statistics. You don't prove something about what hypothesis is true. You prove something about a null hypothesis, i.e. my experiment didn't work, and you prove that that hypothesis is not true. That null hypothesis has either an assumed distribution or a distribution that comes from your data, which we'll talk about, which will answer one of the questions that came up, or 2 of the questions that came up. We started with the simplest example where the null distribution is actually fully known. You know its mean, you know its variance, you have a population underlying model that is completely specified. Rarely the case. But the logic, again, is if there's no effect, then the data I got will hopefully not be way out in the tails. And so that when I get data way out in the tails of this null distribution, then I will conclude that the null hypothesis is false, and then I'll report my data as being significant. I can report a p-value, which is the areas out in those tails, and I can report the data I got plus this odd thing called a confidence interval, which I calculate by adding and subtracting some number of standard errors, and that interval is not, oh, I really understand a model of where my data come from and what hypotheses are consistent with it. Rather, I report hypotheses that wouldn't have rejected it because I composed my confidence interval using exactly the same methods that I composed the interval around the null that led to the rejection in the first place. So it's always this kind of backwards logic. I don't conclude that I don't prove the alternative hypothesis true. What I do is I prove the null wrong. I don't report things that are consistent with my data. I report things that wouldn't reject given my data. So it's always this kind of funny, twisted logic. All the other aspects of frequentist statistics for other hypotheses or other setups are the same logic of null hypothesis, the same logic of p equals 0.05 leads to regions where you reject, the notion of a confidence interval, which is based on the same kind of width, which is based on hypotheses that wouldn't have rejected. That's all still true. What changes is the mechanics of how you compute those intervals based on the underlying mechanics of what your assumed knowledge is. So the assumed knowledge here was that null is known completely. In other tests, you'll have less knowledge. It comes here. Oh yeah, he does this thing about what if we got a result that was a little bit lower. So that's the red bar here, which is closer to 100. And so what if it had been half as big? So this is just, let me get through this stupid build. Yeah, okay. So all this is still the same. Now we got a smaller effect. Now we got a z-score, which is smaller. It's 1.53. We were rejecting if it was as big as 2 or smaller than -2. So we no longer reject. If we calculate the probability outside this value, meaning we have a new value, it's further in, and we calculate the values in the two tails that far out, we get a p-value that's bigger than 0.05, but not by much. And so now all of a sudden we've crossed this arbitrary border of 0.05, and so now in the papers what you do is you say this result was not significant, or sometimes because it's kind of close, it approached significance. It was marginally significant. There are words that we use between 0.05 and 0.1 to say, oh, well, I don't get to write uptown, I don't get the publication, but, whatever. I got close. And so that's kind of the way the field behaves. All right. Wait, there's another build here. What just changed? Another, I don't care. Let's move on. Okay. Oh, God. Every year I say I'm going to get rid of these builds, and then I don't. Make me do it, Arrow, before we keep this thing, because it just annoys me every year. Okay, so significant levels, as I said, are this notion of I got data that are inconsistent with H0, i.e. they have a marginal probability, not just of that value, but of that value or even more inconsistent. So it's the tails. And typically two-tailed, because assuming one tail, of course, if I only care if the drug makes you better, I'd have to know that the drug couldn't make you worse. And of course, before you manufacture the drug, you don't know. You may have an idea of what it'll do. But when you do a one-tailed test, meaning over here I'm not going to reject the null, but over here I will, because all I care about is improving IQ, well then I'm allowed to put 5% over here. Then my rejection's not at a number 2, but a little closer in. I make it easier to reject, which is to say I make it easier to make an alpha error, because I've made it easier to reject. Now I won't reject way over here, but that's the point is that when you're doing a one-tailed test, you have to have an extremely good justification for ignoring data coming out the other way, because you're allowing yourself to make this error effectively more often if the null is true, because you're going to move your thing in.
Could you do one tail with bigger confidence interval?
So the notion of a confidence interval says I trust this thing, give or take this, which means I'm assuming two-tailed as the justification for the interval. The truth may be over here, and it's consistent with me on this side. The truth may be over here, and it's consistent with me on this side. Confidence interval, by definition, is always a two-sided thing.
Or confidence interval with quotes for one tail.
Yeah, it doesn't make any sense. It's just a confidence interval is always an interval in which I'm concluding the probable population mean is within this. I just said words. Those words are false. Okay? We're not concluding about the probability of a hypothesis, because frequentist statistics don't do that. When we get to basis statistics, we'll do exactly that. But instead, I report an interval where if the population mean was any of these and I was testing the data I got, the test would not reject. That's what the interval means, and it's always two-sided.
So if 5% is an arbitrary number, then
Correct.
why don't people use 2.5% for a one-tail test?
That's an interesting question. It would be identical to doing the two-tailed test and then just not reporting it if it came out the other side, which would be weird because consider this drug. If you're going to reject and say this drug is actually working, wouldn't you want to report that if the drug made you worse? That would be fraudulent, it seems to me. So that's kind of a weird thing to do. I understand where you're coming from, which is don't make your test arbitrarily have more power just by ignoring the other tail. But yeah. Okay, so yeah, so that's alpha error, and in principle, obviously, we can pick any boundary here, 0.05, 0.01, and so the field has kind of arbitrary boundaries that you are typically reporting, 0.05, 0.01, 0.005, 0.001. It's all just because we have 5 fingers and 5 toes. It's, otherwise has no meaning whatsoever. It's just arbitrary boundaries. And it certainly does make sense to report the exact p-value because that says something about the exact data that you happen to have collected. And I usually do that. But anyway, that's about controlling this kind of an error. And there are these different words we use: significant, highly significant, etc. Don't remember if there's a slide for this before I again get way ahead of my slides. I'm not looking at slides are coming. To remind myself of what's coming. Yeah, I want to do this now. It's not coming up for a while. What we haven't talked about is the other error. Right? So all we've been talking about is if the null is true, the chance of getting data this big or bigger, or on the other side, is this. But there's the other kind of error, which is there actually was an effect, but I didn't find it. Referred to as type 2 or beta error. Now, that's again something that you can control, and that when you take a statistics course, you'll typically have multiple lectures about controlling this. Let's think about what it is. So, what's the if the null is false, what's the probability I won't notice? Well, in order to talk about that, you have to say what you mean by the null is false. So, if the drug has an effect and the effect is on the mean IQ score, not on the standard deviation, so let's assume standard deviation stays 15. Oh, in fact, I should use a different color. Let's see if this one works decently. Yes, it does. Okay, so the truth, meaning what this drug does, we don't know. But suppose we would like to notice that the drug has an effect if the drug has an effect that is educationally significant, not statistically significant, but actually moves IQ scores enough that I should care, that I would risk the side effects of the drug and would actually be willing to prescribe it to people to make them smarter, if on average it made them smarter enough. Okay? So this is a different English definition of the word significant, meaning it's a meaningful, worth taking a drug for, worth spending money on improvement on average. So that's arbitrary, obviously, but let's pick an arbitrary amount. Suppose, 5 IQ points count enough. Okay? That means the truth is now this. It's an alternative hypothesis. There are many, there's an infinitude of alternative hypotheses, because every distribution other than exactly at 100 is an alternative hypothesis, including 100.005 is an alternative hypothesis. This drug improves your IQ score by 0.005, which is, pointless, right? But it is not 100, so it counts as an alternative. But here's an alternative that maybe has enough bang for the buck that, if it's this good, you'd want to notice. And you wouldn't notice if, by the time you went to here, where you've divided by square root of 15 over the square root of 30, by the time you got over here, you have this green hypothesis, which is centered on something else, 105, same 105, but it's narrower, right? They're both narrower now. And the thing is, you're going to reject here and here, which means you're going to accept in here, right? You're not going to reject the null when you fall in there. But for this hypothesis, this acceptance region has, I need to color it in, where are we going to here? Has this area. In other words, we can calculate, if it's 105, and I base my rejection on 100, what's the probability that I won't reject? If it's 105, what's the probability I won't reject is completely something we can calculate here. And that's beta error. Now, how can we make beta error smaller? What can we change about the experiment to make it so that this area that I've just, I'll do it black, that this area, how can we get that area to be smaller? 105 stays fixed, that's the alternative I'm interested in. 100 is my null, that stays fixed. How can I make that black area smaller? Increase the samples? Yeah. Run a bigger experiment. The bigger the experiment is, this goes down by square root of n. So if you want beta to be a particular value, I want a 5% chance of making a beta error for a specific alternative hypothesis, for 105. Then I can increase the sample size until that area is 0.05. So that calculation, that approach is called power analysis. So what you're doing there is you're trying to make your test sufficiently powerful so that you will reject 95% of the time. So you'll make, it's the beta over here is the probability of an accept. The rest of it's over here. You'd like correct rejects to happen if 105 is true. And so you can make that happen 95% of the time by making beta be 0.05 by increasing the sample size enough so that this is 0.05. And so I'm telling you about this part because this not only is something that you would talk about in the paper in the method section saying we collected this many, our N was 150 people in this survey because we wanted a statistical power of 95% for finding an effect size of 105, a 5-point increase. Now, you'll see that in papers, but much more important, and this is why I'm stopping for a second and make sure you hear this, in NIH grants, they really like to see this. When you describe the experiments you're going to run in an NIH grant, there will be reviewers out there, and it's actually in the NIH guidelines to talk about statistical power and for reviewers to look for your discussion of statistical power. Are you running an experiment that, are you doing enough work and proposing enough work to find the answer that you're claiming you're going to find? Now, there's, again, some really arbitrary stuff under the hood, but in some sense it's a little bit less arbitrary. You have to name how big an effect you consider important. Statistics, frequentist statistics, uses this word significance. Alpha 0.05 significance. If I collected 10,000 subjects on this drug, my rejection region would be much smaller because I collected 10,000. I proved by square root of 10,000. So I would reject for the smaller thing. And I would reject for an improvement of, maybe a half a point. That would be statistically significant. But would it be significant in English? Like, you should take this drug because it's going to improve your IQ by 0.05, by 0.5? Of course not. That will change nothing in your life. A waste of time. So in order to do statistical power, you say, I'm going to look for an effect of this size, which I think will be, meaningful. And then here's how many subjects or trials or whatever I'm going to run so that my beta error is going to be fairly low.
Why doesn't the shaded region go all the way to
It does.
95%?
It does. It's just that it was so small.
No, I mean, so it's going from the mean backwards.
Okay.
All the way to the other.
This is the distribution for my alternative hypothesis.
Yeah.
The null hypothesis sets up the rejection region, which is plus or minus 2 standard errors.
Yeah.
So it sets up a region where outside this region I'm going to reject. And maybe it's here, maybe it's here. I'm acting like it's here right now.
Oh, you're acting like it's here now.
Yeah. So I actually drew this too far. Yeah.
Yeah,
And back in the old example, it was out here.
Okay, so if it
So I
was
could do it there, but I didn't know if I
0.05, then the beta shaded region will go all the way.
Yeah. It would go all the way to this, and it would go all the way to this, which wouldn't look, would look like I could make lots and lots of beta errors.
Okay.
I did, because I didn't redraw it. You notice that this guy doesn't look narrower than this guy by 30 over square root of 15. I should have drawn it that way, in which case I wouldn't have done this. I was trying to have it come out right. But yeah, my drawing abilities were poor. I was just double. Okay, so that's the idea. By the way, this little 2 by 2, in a week, we're going to come back to in terms of what we call signal detection theory. Those of you who are taking grad perception have already seen this 2 by 2. So where you're in an experiment and the stimulus could be there or could not be there, and you could notice it or not notice it. So the logic behind this 2 by 2 is going to come back with the Bayesian approach in a week or so. Week and a half, because I think Anton is teaching it by current standards. It can't be a week and a half. It's not a week and a half. It's Thanksgiving, right? Got the calendar right? Oh, whatever. Anyway, all right. So that's the basic logic. Those are the two kind of errors you're going to make. Oh, and here's the table that I've already had up for the longest time, which I'm going to skip past because it's been up. You've already seen it, but I needed it earlier. Okay. Oh God, another build. Looks like there's still more build, but I can't even see what it changes. Okay. So the logic is you collect some data, you calculate it to a test. You calculate a test statistic based on that data, whose distribution for the null hypothesis is known. And then that gives you a p-value, that gives you a chance of rejecting, and so on. Nothing changed right there, right? I was wondering about that. I get all these builds that are doing absolutely nothing. Hello, am I hitting the wrong button or what? Hello, what's going on with my slides? Hello. Yeah, okay, done on that. Okay, now let's get through everything that Arrow and I have been kvetching about.
Speak for yourself.
Huh?
Speak for yourself.
Oh, no, well, okay, you haven't been kvetching, you've just been making faces.
Right.
So, in your papers, because you're going to have to do this even though it's kind of awful, the fields are slowly moving towards this more modern terminology and this more modern approach, bootstrapping, Bayesian things, the things that we'll be teaching starting after today. But you'll be saying, I got these data, I collected them, they are not consistent with the null hypothesis, I will say they are significant. I may not even put the word statistically significant, because as soon as you say significant, there'll be a parenthetic which will produce your sample value, maybe the z-value, maybe a p-value, or at least a p-bound, like p less than 0.05. So you'll say that. It doesn't mean that you got a big effect. It doesn't say that it's an important society effect. If you ran 10,000 subjects on this NZT trial and you got p less than 0.05, but your sample mean was 100.3, it may be p less than 0.05, so 100 may not be true. But what is true is maybe 100.1 or 100.15. Who cares? So the point is, we're using this word that sounds like it has import, and can be read as if it has import. It's just a statistical model saying you have this confidence that the null hypothesis would be unlikely to have produced this result. Not only that, it doesn't produce any of these values for you. It produces something saying your data would be unlikely to have happened should the null hypothesis have been true. It does not give you the probability that the null hypothesis is true, the probability that it's false, probability alternative. It does not give you a probabilistic estimate of a hypothesis, because it isn't using the logic of probability theory over hypotheses. To do that, you got to do Bayesian statistics, which is where we're headed on days after today. So just understand, it is a language, everybody uses it, but a lot of people misuse the meaning of it, and please don't get caught by that, hence the red flag. Is there another bill here? I don't see anything changing.
So one question.
Yeah.
I'm confused because isn't the alpha level the probability that the null hypothesis is false?
It's the probability that if you got a value outside, no. The alpha 0.05 is, if the null hypothesis is true, here's the proportion of experiments that would give you values that wild. That's all it is. That's the only probabilistic model that gives you 0.05. If the null is true, you will get values out here, alpha % of the time. That's what alpha is. It is a probability. It's not a probability about a hypothesis. It's a probability of data sets, if you collect data sets over and over again, like the one you collect. Meaning p-value, meaning of CI, I've talked about those. Okay, so now let's talk about the menagerie of other tests. So, it was asked, what if the variance that I got is different than, the standard deviation that I got in my data was different than 15 by a lot? What if I didn't know the population standard deviation? What if I didn't know the population's mean? What do you do then? So, first you calculate a number of other test statistics. So, this looks a bit like the Z calculation, something minus the null hypothesis over something like standard error. Except one thing has changed, which is I got S here instead of sigma. So generally, we don't actually know what sigma is. We don't have IQ scores which were designed from time immemorial back in the 1950s to have a standard deviation of 15. We're just giving rats time on a maze to solve a problem, or having graduate students in a dark room pushing buttons, or whatever it is, electrode measurements over multiple days over multiple neurons. Whatever it is, data that we collect, we don't know what the standard deviation of the population is. We don't have a model for that necessarily. Maybe we have a Poisson model for neural firing, and so we are willing to posit a population standard deviation, but usually we get an estimate of that standard deviation from the data itself. And so we calculate a statistic. Now this statistic looks a bit like the one you saw in descriptive statistics, called the sample variance. The one thing that has varied from it, which we will return to probably on Thursday, is the n-1 downstairs. So in frequentist statistics, you always see these n-1s all over the place in various descriptive statistics that we use for estimation and for inference. The reason is, the way we calculate, the way we'd want to calculate this is we would take xi minus mu. How far are these numbers from the mean? I'd like to know the population variance. And the population variance is how things differ from the population mean. Population mean is mu. We don't know what mu is. Our best guess at mu is x bar. But x bar is not mu. It's just the mean of the data I happen to collect, not the mean of all the population's data. So the x bar is not mu. Not only that, the x bar is designed to be the centroid of all the x's, because that's what a sample mean is. Which means, on average, it's closer to the x's than mu is. Mu may be closer to some of them, x bar being closer to the others. But over the group, x bar is closer to them than mu is. Which means the sum of squares upstairs, as compared to compare the xi's to mu, is going to be underestimated. It's going to be closer to x bar than it is to mu. So if you divide by n, your estimate of the population variance will be biased low. On average, if you do it over and over again, the numbers you're going to get for s squared over lots and lots of attempts of doing that will on average be smaller than sigma squared. And it turns out the n-1 fixes that. In a later class, not today, we'll prove that. It's a fairly trivial proof. But the point is, the n-1 is down here to make this a statistic whose expected value is sigma squared. A thing you can calculate that on average will be sigma squared. It'll be noisier, but it'll be sigma squared. It'll be accurate, but it'll be less precise. So in frequent statistics, you're always using these estimators of population statistics that are designed to be unbiased. As you see n-1s or n-2s, where the -1 is subtracting what's called a degree of freedom. when I collect data, let's say n is 30, like in the last example, so I collect 30 of these guys, okay? They could be anything. They could be 115, they could be 112, they could be 97. So there's 30 degrees of freedom in the data. But now I'm comparing them to x bar. And now I'm treating x bar as fixed because I calculated x bar. So now, if you told me x bar and you told me 29 of your data points, then I know your 30th data point. Why? Because I know they have to add up to x, they have to average to x bar. So I can, and there's only one value for the 30th data point such that their average is x bar, which means I only have 29 degrees of freedom in my data. I lost 1 degree of freedom by fixing x bar and acting like it's truth. And so that idea of degrees of freedom travels around in statistics and is often an intuition for what you should divide by that matches what gives you an unbiased estimator. So this was 30. I subtracted 1, I got 29. 29 of my xi's were free, but if you told me 29 of them in x bar, I knew the 30th, so you don't need to tell me the 30th one. So that's another way of thinking about what n minus 1 means. Regardless, this gives me an estimate of sigma squared. Its square root is called s. We had sigma here in the previous formula. Now we're using s instead. Now, before I took x bar, which I knew was going to act like a normal distribution, and I subtracted 100, which is a constant, so it was still a normal distribution, and I divided by sigma over the square root of n, which was another constant, not varying with my data, it was just a constant. And so I took standard normal, subtracted a number, divided by a number, so it was still a normal distribution. Okay? But now we're moving to a new statistic. The new statistic is called t. The statistic is computed by taking my data, computing its average, and the same data, computing a sample variance, taking a square root, getting a sample standard deviation, and calculating something that looks like z, except that upstairs is a random variable, x bar is a random variable, collect a new sample, you get a new x bar, and downstairs is a random variable, collect a new sample, you'll get a new s. Okay? So it's no longer a normal distribution, because it's a noisy thing divided by a different noisy thing. And so it will be noisier, and its distribution will not be Gaussian, because it's one noisy thing divided by a different noisy thing. And its distribution will depend on n, where if n is really, really big, this guy won't be very noisy, and it'll look more and more like a normal distribution. But if n is small, if you only collect 5 data points, or 10, or 20, then this will be noisier than a normal distribution. So that distribution is called the student's t distribution. There's a build happening here that's not actually building anything. Okay, it has to build. There we go, got it has to build, but you didn't know so there. So we don't assume we know sigma, so we do our best to estimate it. That's saying what I just said. And so now, this thing doesn't act like a normal distribution. I can use the same logic as everything over there, except instead of putting here the normal distribution, I have to put here a different distribution that takes into account that the denominator is noisy. And that different distribution is called the student's t, because the person who discovered it published pseudonym, how do you say that? Under a pseudonym. As student. Arrow, was it a group of people? A student, one person, or several people?
It's like one guy working at the Guinness factory.
What's that?
It's like one guy working at the Guinness brewery, or something like that.
That's true, and I think it is one guy. I'm not sure if one. What, Guinness didn't want him to publish? Is that why he was student? I should know these stories, so I can tell you stories, but I never remember these stories, sorry. Pascal would have spent a half hour on this if he were here. I could say more, but I won't. Anyway, point is, this distribution is not one distribution. It is a parameterized set of distributions parameterized by n. Actually parameterized by n minus 1. And so you look in the back of your stats textbook, and it'll have tables of the t distribution where there'll be cutoffs for various probabilities, where to place these guys, and they'll be different depending on n. And then it'll pass back the probabilities to you. But otherwise, all the other logic is identical to what I talked about, You have a null, you have boundaries, you reject or you accept, you calculate a confidence interval using 2 of these instead of 2 of the other one. The bounds, remember I used double of them? That came from the standard normal. When you use the t, how many of them you have to go to the distribution to find out how many? Okay, so it's a little bit extension of the logic, a little bit extra mechanics. This is an overview, so I'm not doing examples. That you can get in the stats class, or if you need to do it next week, come talk to me, I'll tell you how to do it. But the point is, all the underlying logic, null hypothesis, data not consistent with sufficiently not consistent with the null hypothesis that we reject, confidence interval being those population means which wouldn't have rejected the data you collected. All of that logic is the same. It's just that the test statistic is noisy in the denominator and you have to account for it, so you allude to a different distribution. And other than that, it's all the same. The t-distribution doesn't look like the standard normal. Oh, here it is. It's an animation. So as n goes bigger, the t-distribution looks more and more like a standard normal. But at first, when it was n equals 1, it had much bigger tails because you're dividing by this noisy number, and so bigger numbers happen. Okay? And so it's the same logic, but you have to refer to a different distribution. What's going on here? Hello. Oh god, I need to build. Oh my god. Am I done? I think I'm done. It looks like there's more build, but I don't see any. Okay. We sometimes want to test proportions. Think of how many times they press this button versus this button in some experiment where you got a graduate student in a dark room pushing buttons. Okay, so that means it's the binomial distribution. And earlier today we talked about the binomial or the coin flip distribution, which doesn't look anything like a normal. But if you collect enough button presses, it looks like a normal. And so that means that you can refer to the normal distribution again. So the sample mean is just how many times did they hit this button out of how many times they press buttons. I hate to say the fact that what we have here has n and m reversed from the n and m's I used earlier in the day. Is that true? Yeah, I had m heads out of n crosses last time, I think. Maybe not. Anyway, if I did, my apologies for being consistent with later slides. So, for example, you may ask, is this coin biased? Or, more relevant example to those of us who do behavioral experiments, is this observer biased? So you've run a long experiment where everything's nice and randomized, but you're worried about whether my subject was biased to, say, interval 2 in a 2-interval forced choice experiment. And so even though interval 2 was the right answer only half the time, were they on average biased to say interval 2? And so you could take the proportion of times they said interval 2 and say, was it different than 1/2? And so that would be a binomial test. And the exact test would be to refer to the binomial distribution. But a really good approximation that's much quicker, that uses all the logic we were just talking about, is to take the proportion you got, compare it to the null hypothesis of 0.5. And to do that, we need to know how this behaves as a normal distribution, which means we need to know its standard deviation. And it turns out that the variability of a single toss of a coin is square root of p times 1 minus p. Often when you refer to the binomial, you refer to, if p is heads, tails is 1 minus p, and you refer to that as q. So if you just calculate the variance of a coin flip, which is a really easy thing to do because there's only 2 outcomes. So you use the formulas we've had all along for computing a variance. The variance of a coin flip is square root of p, the standard deviation, of a coin flip is square root of pq. And so if your null hypothesis is some particular proportion, like 0.5, so then you can get a z statistic, just like we were using 20 minutes ago, by taking the proportion you got, comparing it to the null hypothesis proportion, say 0.5, divide by the standard error, which you can get straight out of, so the square root of the number of tosses is the same as it was before. That's the square root of n. And this is the standard deviation you started with, which in this case is the square root of 0.5 squared, otherwise known as 0.5. Okay? And so that number, which is noisy on top and is constant and constant, will act like z as long as the number of trials is big enough. It doesn't have to be all that big. 40 or 50 is just fine for this being a very, very decent approximation. And so then you can use all the logic of the z-test that we talked about in the first hour for something that is not normal at all, but is just coin flips. And you don't have to just compare it to 0.5. P0 and Q0 could be things other than 0.5. It'll still work. If you want to go way off 0.5, like compare it to 0.999 or something, well, the approach to a normal distribution for 0.9999 takes a lot more coin flips. And so I would suggest you not do that there. But the underlying test could be done with the binomial distribution, the exact distribution, rather than this approximation. Okay, so that's another example of a test for a different kind of data. That didn't do anything, right? What do we got coming here? Oh my God. Did I go too far? No. Good. There's a menagerie of other standard probability distributions that are often derived from distributions we know about. So if x is standard normal, if you took this variable and squared it, that's a random variable. It's always positive, right? Because it's a number that you squared. So you took the bell curve and you drew numbers from it and squared them and then say, what's the distribution of that? Those will all be positive. And it turns out that that is a distribution, has a name. It's called chi-squared. If you take a bunch of them and add them together, drawn from the same distribution, so that's referred to as a chi-squared distribution. It's an exact distribution. It's a distribution of a very specific process. But it turns out that that distribution often approximates the distribution you would get from various calculations that you might do, some of which are statistically useful. So for example, suppose I have a discrete distribution across various outcomes. Let me just start this clear. Suppose I have discrete finite category data. So I, do a survey of a bunch of people, and I put them in various categories, maybe job categories or something. I don't know, some categorical variable, and I get a histogram of how many people fall in these different categories. So this is a discrete distribution. This is a histogram. So 5 people are here, 12 people here, 3 people here from the people that I surveyed. And suppose I'm asking from this population I surveyed, the people that are living in Connecticut, is the distribution of jobs significantly different than the distribution across the United States generally? And so I have a population distribution that I expected, which maybe was flat. It doesn't have to be flat, but I'm just making up an example. So the green is a population, and black is sample data. I'm asking, are the sample data different? Meaning, is Connecticut got a different distribution of jobs than the United States generally? So there's discrete data in categories. And so you can basically make a test statistic that says, how different is this from this, this from this, this from this, this from this, this from this? Effectively, what you do is you take those differences, square them, and add them up, but I'm not going to go through all the mechanics. I'm just going to say, when you do this calculation, you get a test statistic, and it turns out that it is chi-squared, where the number of degrees of freedom is the number of categories minus 1. And so you can use the same logic. There's a number you can calculate from a set of categories and a histogram of the way they were distributed, comparing them to an expected distribution, and asking, do they differ? Is the Null Hypothesis, which is the green thing, rejected because these data are so different from it? Same logic, same idea. You wouldn't talk about a confidence interval on this because the test statistic isn't kind of interesting, but you would be able to do the significance test saying, no, these data are so different that I think there probably is more there, probably is less there. Okay, so that's a goodness of fit test. Test of independence, same idea, but the table I'm putting people in is categorical, discrete, but there's two different variables, so they're falling into a table. And so I sampled a whole lot of people and asked where they fit on, I don't know, hair color and occupation, some nonsense. Two variables, and you're asking are those variables independent. And by independent, I mean probabilistically independent, meaning tell me about hair color and you're not learning about their profession, or whatever the hell the two variables are, okay? So what you do is you take the distributions on the margins, you multiply them, and if they were independent, multiplying them would give you what's in the table, because right, P of x comma y is P of x times P of y. So you use probabilistic independence to predict what should be in there, then you got what you actually got in there, then you ask how do they differ? You calculate the same statistics you had for this, which is you have a green distribution across these boxes and a black distribution, green being expected from the margins, black being what you actually collected. You compare them, subtract, square, add them up, basically, and compare them to a chi-square distribution. And it turns out that that's approximately a reasonable thing to do as long as none of the bins are almost expected to be almost empty. Okay? So, asking whether a variance is bigger than an expected variance. That was a question asked, well, it wasn't exactly what you were asking, but what if the variance after NZT looked like it was different than 15 squared? What if the standard deviation looked really big? One question you might ask is it really big? Is this drug actually having an effect, which is it's making some people have higher IQs and some people have lower IQs. It's not having an effect on the average, but it's doing something to people, and it's increasing the variance. That's a reasonable question to ask. You can calculate S squared, this sample standard deviation, sample variance, and you have sigma squared null hypothesis, which is 15 squared, and you can ask, are they different? So S squared over 15 squared will act like a chi-squared. So you can actually go off and check. Is this variance bigger than this other one? So I can take variance A from a sample, variance B from another sample, and take their ratio and say, is that different from 1? So a chi-squared, which I said was a bunch of standard normal squared, divided by another chi-squared, which is another standard normal squared and summed, that, it turns out, is another distribution. It has a name, the F distribution. Like the chi-squared, it has parameters. How many guys are you adding up in the numerator? How many guys are you adding up in the denominator? And you can use that to compare one variance to another. And it comes up, for example, in a statistic that you may have heard of called analysis of variance, where you vary different variables and you ask, does this variable have an effect? Does this variable have an effect? Do they interact? So, again, the distribution comes from probability theory. It comes from you have random variables and they're behaving this way. Then you do an experiment and do a calculation that effectively is calculating a variance two different ways and calculating their ratio. Finally, there's a big menagerie of tests that don't assume what the distribution is underlying them, and then just use the order of variables, but not the actual differences. So it doesn't take differences and square them and adds it on, but just takes their orders. And so they're generally weaker tests. It's harder, that you need more convincing evidence to get them to reject, because you're not assuming normal, you're not assuming, some continuous distribution. Just asking, did the order of the things, are all of these guys bigger than all of those guys, or something like that. All right, this is a good place to break. Done with our frequentist statistics, and we will move towards the modern method on Thursday.